Okay, so I will talk about modeling and simulation, and today's agenda is we'll start with the introduction to CIDETEC energy storage. Then I will mention some motivation on this study. Then I will basically focus on cell modeling, different aspects and how we are answering to certain requirements in the cell developments through the modeling aspects. Then there will be like two part of Q&A session in which you can reach me making the question you want or you think I should answer to you. Then we will like to mention some of the software landscape we have identified, and also we would like to take the opportunity to introduce you our tool Proteo. And then there will be like a wrap-up session. So first, I will start introducing CIDETEC. So in the end, there's one organization for applied research, but we are three leading institutes. One is CIDETEC Surface Engineering, the other is CIDETEC Nanomedicine, and the one we belong to, CIDETEC Energy Storage. What our approach is to reaching the gap between R&D and the industry. And our mission is to give value to the industry. It's a target-oriented approach, and we develop technology transfers. And we say that our lemma is from powder to power. So we start from new material technologies and materials. Then we go to the manufacturing at pilot line level up to battery cell. We also develop battery systems, developing prototype modules and battery packs. And then we also are working on the energy storage application. And there are then two other research transversal activities. One is the modeling side, and the other one is the testing and the characterization. So coming to the motivation, so the current situation is showing this graph very properly, and the thing is that there are several forecasts on the demand of batteries, and apparently it's substantially increasing the demand of the batteries. And the thing is that apparently it will go from the 30 to 50 gigawatt hours to reaching in 2025 between 150 and 300 gigawatt hours of value. And also there's more forecast and increased value on the 2030 expectation on the 2030, in a way that it's expected to have a demand on between 400 and 1,000 gigawatt hours. This is about the demand, but then there is another forecast and new announcements that we have recently heard, and is that the battery production is also expected to increase across Europe. And what is expected to happen that by 2030, there will be like 800 gigawatt hours of battery production in Europe. So this is fascinating, but obviously it's required the speeding up and improving of the battery manufacturing. So how, So we need to speed up and we need to improve the battery manufacturing, and obviously we can handle by different approaches. And one of the approaches is written below, and it says about, first, we think that we should minimize the trial error approach, but by gaining more understanding on the manufacturing process and the correlation between different steps and impact on the intermediate and final products. Then the second is that obviously we need to parameterize not only at the cell level, but also manufacturing level, all the steps properly. And it would be good also to work on reducing the time to, and also the experimental work for this parameterization. Also, we need to enhance the, we need to enhance the battery cell performance, and this can be achieved by gaining more understanding at the cell level and also identifying the degradation mechanisms, so that we can minimize, certainly by developing and controlling the usage scenarios and so on. And also we should optimize the cell design. So today, I will be focused on the last 3 points. And what we think is that this can be certainly achieved or held or support by multiphysics models, that indeed they need to be accurate, robust, and computationally efficient. Okay, talking about the cell modeling, we had the yesterday part 1 training in which you were able to see that there are certain different scales in modeling the cell, and obviously each of the scale can provide certain property or certain information at a certain level of the material, electrode, or cell level. So I like this plot coming from this reference, in which they link at different scales the computational efforts, also experimental work, and what is expected to obtain by each of the scale. So we have enumerated different approaches and different scales in which for each of the scale you obtain certain information. And today I will be focusing on the continuum scale, which is most of my background is in this area. So yeah, for the continuum scale, as you saw yesterday, most of the continuum scale falls into the two categories. One is the electrochemical based and the other one is empirical based. Coming to the electrochemical, we can classify between the P2D model and single particle models, while the empirical models can be classified between data-driven or artificial intelligence implementation methods and equivalent circuit model. So here I will start just showing some baseline in this area, but I would like to focus mostly on the extensions of each of the sections here. So taking into account the basic P2D models, we have make some extension to this reference model in a way to capture certain mechanisms or certain behavior of the cell that I will explain later on. And in the same way as we will be doing to the P2D model, I will be focusing on the extension on the single particle, and mainly on the single particle, including the electrolyte domain. For the data-driven models, I will show one example of our implementation basically built for cell design purpose. So now coming to the P2D model, as I said, we have like different extensions or variation or implementations in order to capture different mechanisms or different aspects into the continuum scale. So I will talk to the coupled P2D plus 2D model. I will also talk about PXD model, which is a extension of the dimension of the P2D model to P3D or P4D scale. Then the P2D model, including certain degradation mechanisms. I will also talk about our approach in the PXD, including mechanical aspects. In the same way as I will talk about the P2D model, including thermal aspects. Then we also solve the P2D model in frequency domain to capture the EIS spectra. And then I will mention our last achievement on the surrogate models. So as you heard from yesterday seminar, the P2D model is the most common continuum scale model and rests on the porous electrode theory, concentrated solution theory, and kinetic equation. It's very well known in the lithium-ion community and investigations. And in principle, it's relatively accurate and it's computationally quite efficient and usually have shown good agreement with the experimental data. You have some references included here in case you want to check this information. So these are the equations, the governing equation of the P2D model, one related to the mass balance in the electrolyte phase, the charge balance in the electrolyte phase, Then there is a mass balance in the lithium of the solid phase and the potential charge balance in the solid phase as well. And then also we should also include the kinetic, which is basically takes into account the intercalation of the lithium, and it's modeled by the Butler-Volmer equation. So these are some of the captures of the internal variables of our P2D model or our P2D code written in Python. So this is an example of the graphite NMC622 cell in which we have applied, it was fully charged, and we apply 1C discharge at 25 degrees. So these are the internal variables at the time of 0, so when it was fully charged. So you have here the electrolyte concentration that it's uniform along the electrode separator and the positive electrode, which is cathode. Then this is the initial value of the ionic potential, which is set fixed at the beginning of the discharge. And then the solid or electronic potential, we fix 0 at the anode phase. So this is the potential of the OCV at the very beginning of the cathode and the just cathode. And this is the intercalation rate or exchange current density of each of the electrodes. Okay, and this is at the time of 0. So in the end of the simulation, that in this case, it took like almost 1 hour, 3,580 seconds. So there was a discharge profile. So we see this gradient on the electrolyte concentration, which is typical on the liquid electrolyte. Then this is the value for the ionic potential in the end of the discharge. You can see now here the value for the anode phase and the cathode as well. And you can see here the electronic potential in the end. This value would be for the graphite in this case, and this is the discharge state of the NMC622. And these are the exchange current density for the, again, anode and cathode in blue. So this is the baseline, as I said, for the P2D model, which is our P2D model. We wrote it in Python, and we usually solve the equations by finite element methods. And for that, we usually use a library, open source library called Phoenix. Okay, so then one of the extension and the reality is that we have seen that the certain cathode materials have different, more than one active material. And basically is that usually they mix two materials in order to have the advantages of each one and avoid the disadvantages of each material. So for instance, we have seen blending LFP with spinel cathodes, or so we wanted to capture this blend electron behavior. So we modified the equation so that we could capture this multi-active material electrode. So in this case, you can see in red the modifications in the code for the base P2D model, and what we made it in a flexible way that we could include from 1 to M active material either on the anode or cathode domain. So yes, these are the equations. Again, we solve them by Phoenix in the Python library, and this is an example of the results we got for the blend electrodes. So in this case, we took the data from this reference, and in that case, they were comparing graphite NNC 100% NNC with 100 LMO, and then with X or certain value of LMO plus 100 minus X NNC. So these are the voltage drop or voltage, yes, we have seen at the condition of C/2 at 25 degrees, and which is really interesting to capture the evolution of solid concentration for each of the material. So yeah, I think it's a very good approach in order to get more insight on bled electrodes. Another aspect in the battery domain is that we usually use EIS spectra to get more insight on the cell performance. So we perform EIS. By doing that, we can identify resistance contributions, even identify the main contribution in the resistance impedance. So you can correctly capture which are the main limitation in the voltage domain. So we wanted to understand also or link the experimental EIS spectra with the model-based spectra. So what we did is that we modified our P2D model, which is in time domain, to the frequency domain. So at that point, we insert the sinusoidal time domain equation, and our code can capture or can insert or even current or the voltage as an input, and then get the other. So it's flexible in that way. We can capture CC profile and also CV profile. So yes, then we insert the sinusoidal spectra and we run the simulation in a very large or wide range of frequency. For instance, from 1 millihertz to 1 kilohertz. And so what we did is to transport the time domain to this frequency domain by applying fast Fourier transform. So we got something like this spectra, and then analyzing the first harmonic, we were able to capture the EIS spectra. And to show you an example, here you can see the comparison between the data obtained through this paper, which is referenced here, and our code. So the simulation run by CIDETEC is written in orange, and this is the Nyquist plot in which you can see the impedance in the imaginary part and real part of the impedance, and compared to the simulation that was performed in this publication. And in terms of impedance, the results mimics the literature data. So we think it's a very interesting approach. Then, as we are also analyzing the battery by EIS, and then trying to correlating with the model-based spectra, we can capture or identify the main limitation, and then know exactly which are the developments we should or be focused on the improving, or with the target of improving certain performance. Yes, another aspect which is critical for us is the depending on the material, you might be facing some mechanical stresses. I'm thinking now in the silicon phase, which is depending on the lithiation state, might swell or compact, depending on this lithiation or the lithiation state. So what we made a certain modification to the P2D code based on these two papers in which they were proposing that these lithium concentration gradients could stress and force the swelling. So we include this modification in the code, and then we were able to capture the thickness change. So you can see now here two plots in which we compare the voltage drop of our simulation against the simulation performed with this paper references here. And also we compare the thickness change of the electrode in which that we obtain by implementation of this model, and then the results that they obtain in this paper as well. This is obviously a very important issue if we want to address these mechanical aspects, and then if we want to track the impact of this mechanical swelling on the degradation. So it's like a first step in order to capture the certain mechanical degradation mechanisms. And then coming to the PXD, the thing is that it's completely different to analyze a very small cells or higher large cell scale, in a way that in the large cells you might be facing some heterogeneity in the temperature, and it's critical, this heterogeneity or not homogeneous distribution of the temperature, because it might be affecting again on the certain degradation that can be more severe in certain areas that might have a higher temperature than compared to the other areas. So we extend the P2D model in order to capture different dimensions of the cell. And in this case, we have this P3D model, in which in the P2D model, you have the thickness of the electrode, and then this is the active material. Then in the P3D model, you have the thickness of the electrode and also the length of the cell. While in the P4D model, you have the thickness, the length, and the width, which is in that way we can capture properly the heterogeneous current distribution and also temperature distribution. So these are some of the samples we got from our P4D model. So in this case, it's a monolayer cell, so only one sandwich of electrode. But we can see that we can analyze certain design properties like the tag location. Obviously, we can play with the geometry, and also we will be playing with the sandwich numbers, which is jumping from monolayer to multi-layer approach. So this is the electronic potential we got at that point of the discharge profile, and this is the mesh that we applied in our code. And then, sorry, I'm not able to see now. And this is the electrolyte concentration, which is higher at the cathode, so it will be charging profile, and lower in the anode phase. And this is the electrode utilization of the solid concentration along the two different anode and cathode electrode. And now I have a video. I hope you can see. It's really quick. This is just about how the concentration of the electrolyte is moving, and also captures the contraction of the anode phase, because here we already implemented these mechanical aspects due to the lithiation state. So we were able to capture this compaction of the cell. Following with the large cells, it's important to track the temperature distribution along the cell. So in here, we couple the P4D model to the thermal model, so capturing this thermal behavior. And in this case, in the heat source, we had this the heat coming from the reaction reversible, then also reaction polarization heat, and also including the omni heat generation. So by having this model, we are able to capture this temperature distribution, as I said, which is very important aspect in designing the cell and trying to enhance the lifetime of the cell. Another approach of this P4D model coupled to the thermal model is that this simplified version, in a way that we couple the P2D model to the 2D thermal model. So here you can see the schematic of our cell, in which we would have the current collector here, from the negative part, the positive current collector, and then our P2D model, and here is called 1G. So basically this figure comes from the lithium metal solid electrolyte battery, but it would be exactly the same for the lithium ion, in which we have the this exactly the same domain, but with the difference of the lithium metal and the graphite. Obviously, in which the lithium metal you have a stripping plating, and in the graphite you have intercalation process. So basically, in this configuration, we solve in a iterative way the mass charge of the 2D dimension along the cell or current collector, which would be from one side the anode and for the other side the cathode. And we solve it in an iterative way with the P2D model, because they are somehow correlated in a way that the current goes from the taps to is along distributed in the current collector, and then it will be certain current from this point to the electrode separator and comes to the other end. So this is another approach. It's computationally talking, it's more efficient, but we applied the two options in case we want to have something like very quick and get information on the temperature distribution, or we want to have a very accurate model. So, but both aspects and both approaches are really important to have. So, and here we have an example in which we use this P2D model hooked to the 2-3 model, and in that case we validate the model against graphite NMC 622 monolayer cell, and we wanted to study 3 size cells. So we played with the length of the cell from 100 centimeters to 200 centimeters and 300 centimeters. And then we analyzed the evolution of the temperature in 4 different nodes that are shown here. So basically, what we observed is that in the case of a very not large, or this case it was with 200 centimeters long or length cell, we weren't able to observe much heterogeneity between one node and the other, while having this higher length cell, we were able to capture this heterogeneity in the temperature. So this is very critical and also very important for us, because we can also test the cell in this, setting the sensors in this place, and then we can validate the code and then again improve the cell, knowing exactly or understanding properly which are the main critical aspects that provokes this heterogeneity in the heterogeneity of the temperature in the cell. So, and this is about the degradation. Obviously, the P2D model has been extensively used for predicting life and understanding certain mechanisms. And in here, we also did some work in those aspects, and these degradation mechanisms that are presented here included the SCI layer growth. And in that case, we took all the data what were taken for one commercial cell that was analyzed at CIDETEC, and then we did some postmortem activities in order to capture these mechanisms. So we include the code and insert the proper parameters value in order to capture this capacity fade depending on the cycle number. So at that point, these are the capacity fade profiles at C/2, 25 degrees. And we are able to capture SCI layer growth, active material loss, and then also a lithium plating through the Butler-Volmer equation as well. Modification of the Butler-Volmer equation. And then I talk about the P2D model. I jump to the single particle model, which will be much simpler. And then I will jump to the data-driven models. So as I said, single particle model is like a simplification of the P2D model, but then you also only take into account the diffusion of the solid phase, and you ignore or you don't take into account the electrolyte phase. So extremely used for certain applications such as the BMS or temperature, including thermal behavior, it's good to identify certain thermal properties as well of the cell. So yeah, this is the two main assumption of this single particle is that each of the electrode is modeled as a spherical active material, and we ignore the electrolyte phase as it's shown in here. You might have seen these references in case you want to have more information. And this is our single particle model in which, as I said, we model the diffusion by the Fick equation with the corresponding boundary conditions, and then we get the voltage of the cell. And then we also did some work implementing electrolyte equations into the single particle, and it's called single particle model with electrolyte, SPME. So in here, we are taking into account this electrolyte phase, mass balance of the lithium in the electrolyte, and we are also capturing the voltage. And here I wanted to show you some comparison we made at low C rate and high C rate condition, in which we see that if we run the simulation at very low C rate, that can be like C/10 at 25 degrees, we don't observe any differences in the voltage domain. And if we compare the electrode utilization or the solid concentration, there's not much difference on the three models described before: P2D model, single particle with electrolyte. And however, if we perform the simulation at higher C rate, and depending on the thickness of the electrode, high C rate can be 1C, is that we observe certain variation of the voltage drop voltage profile. And this is mainly because at certain thickness of the electrodes, you might have certain limitation on the electrolyte. So as in the single particle, we are not taking into account at all the electrolyte limitation, and in the single particle electrolyte, we are taking somehow, it's a bit difficult to use this simplified version to certain applications. But in any case, depending on the application, are good enough, and obviously they are much more efficient in terms of computational efforts. So if we compare the computational effort of our P2D, it might take like around 20 seconds to solve 1C profile in a current lithium-ion battery, while for the single particle, it might take less than 1 second. So depending on the application, it's critical to use one or the other. And then I wanted to mention something on the surrogate models. Basically, the surrogate models can be classified into these two options, but the idea here is to have high fidelity model that can be, for instance, our P2D model. So we run the simulations, and we have this data coming from the simulation data, and then we can either go for this surrogate models or the machine learning approach, or reduce all the models. So the machine learning approach can be like linear regression, Gaussian process, or even neural networks. And for the case of reduce all the models, we can apply PGD, POD, TPWL. So I will briefly explain later on each of the options. But now I would like to mention one of the activities we performed in the surrogate models. The idea was to build a model in order to automatically solve the optimization problem. So what we wanted to have is like a dragon plot depending on certain parameters. And as I said, the P2D model might take like each of the simulation might take like 20 seconds. So common optimization algorithm might take around like 5 hours to get a result. So what we thought is that we wanted to try to improve the efficiency of the code by building a neural network scheme. So at that point, what we had that is that we wanted to have an output like the energy density and power density, because in the end we wanted to draw the Dragon plot for certain parameters. And the inputs we modified are like the one listed below. It's electrode thickness, porosity, particle radius, separator thickness, and porosity, and also the electrolyte initial concentration and ionic conductivity, and obviously the applied C rate. Okay, so playing with these parameters and trying to maximize the certain energy or power, it might take a long time. So we performed these two approach neural network. And the first neural was developed in order to classify in, first we ran the simulations, obviously for the P2D models, and what might happen in the P2D model is that at a certain condition, you don't finalize until the end of simulation. And this is mainly because you might have certain limitations, for instance, electrolyte depletion or whatever. So we classify like, one is that it ends the simulation, 0 is that it doesn't end the simulation. And for the case of the simulation is finalized, we wanted to predict the value of energy density and power density. So we built two neural networks, as I said, one for classification and the other one for prediction. And in this case, it was a first trial. So it had the classification neural network has like 2 layers, and each of the layers has the first layer 10 neurons, while the second layer has 18 neurons. And for predictions, we have another 2 layers, and the first layer has 24 neurons and the second 38 neurons. Okay, so now I'm going to show our results in this specific case. So for the case of the classification result, as I said, 1 is that the simulation is finalized by the P2D model, and 0 is that it's not finalized. So we built this, we trained the neural network, and then we test the neural network, and these are the results from the testing. So sorry, I cannot, yes. Now you see this plot here, and so you can see distinguish between the true, positive, false, positive, true, negative, false, negative. So what we want to have obviously is that as much as true positive and true negative values, which are basically this one is the true positive, which were the 98, and then this value is true negative, is that it predicts negative while it's true, and in this case true positive is that it predicts positive, that it's 1 and it's true. So we achieve like a very good results with this very preliminary approach on implementation of neural networks for classifying in this case. And then we wanted to predict the energy density and power density for the case that we achieved the 1, that was the simulation was finalized. So in this case, we again evaluate, we train the model, and then we test the model, and then we compute the error that in this case we achieve this 3.5. This is an example of the usage of the surrogate models, and it's just to show that the capabilities of this kind of models in order to make more efficient the computational code. So, and this is about the data-driven models. So comparing to the surrogate models, in this case, we are treating the experimental data, or data coming from the, let's say, real world, real batteries or materials or whatever. And the workflow is that basically similar to the one in the surrogate models, but obviously we have this raw data and we need to perform the data preparation. We need to identify the features of the model, features or parameters. We need to identify the outliers. And then obviously once we make this data treatment, we identify the proper models. And then once we develop the models, we train the model, and then we test the models. And this obviously can be in a iterative way in order to have very accurate models. In terms of types of machine learning, we can have like supervised and unsupervised model. So supervised is that this data has labels, while in the unsupervised models, this data doesn't have labels. So in the case of supervised, can be for classification, as we showed previously, and then also regression, which is predicting certain values. And in the case of the unsupervised, we can have like clustering option. So, and here what we have done is that we have recently started working on implementing data-driven models. So we took data from this paper. Sorry, I think I forgot to include the paper, but it's from the Severson paper. So we took the data coming from Severson paper, and first we identified the features, analyzing these capacity fade values, but also voltage profiles, and also coulombic efficiency of the results. So first we identify the features, then also we identify the outliers and try to minimize these outliers or avoid them. And then we make some trials with the LSTM that also I think was mentioned yesterday. So the idea of this work, it was to predict early prediction of the cycle life. So only analyzing a very low number of cycles, we were able to predict the cyclability of this cell, which I think is a really powerful approach in order to avoid certain or reduce the number of experimentation. Okay, so the second part of my session is basically focused on the application, different applications. So you might know different applications of the continuous scale, like the online monitoring, optimization, aging prediction, safety analysis, and parameter estimation. And today I will be focusing in 3 examples. So these are 3 of the aspects we've been working, and the first 2 were materialized into different publications, and the third is still running, and we are improving the code. But the idea is to come up with certain publication. Okay, so the first one is that we implement certain, we identify certain dimensionless parameters to optimize battery performance. So I will show the results we got at that point. Then another approach on machine learning algorithms with this similar approach of I already showed in the performance predictions. And then model-based parameterization, which I think is very important aspects in the modeling, and it's not tackled much at this point. So the first sample is on the use of dimensionless parameters for fast battery performance analysis. So what we did at that point was, based on the P2D model, we identify or we derive dimensionless parameters. Analyzing these dimensionless parameters, we identified the limitation of the cell, and in that case, we were analyzing in-house solid polymer electrolyte cell. And with these parameters and the limitation we identified, what we did is to provide some guidelines to improve the cell performance. And then what we did also is to validate the predictions by numerically from the P2D model, but also experimentally, which I think which I found really interesting. So these are the parameters we identified for the case, I mean, based on the P2D model. I'm not going to go in detail in all the parameters, but basically what we took into account is that the 4 equation of the P2D model, we skip the thermal behavior, but we capture obviously the dependency of the parameters that might have over the temperature and stoichiometry. So for the 4 equations, we got the number of dimensionless parameters. And then as we did the parameterization work for the cell study, and in this case, it was lithium with PO, LiFTCI, and LFP as an active material cell. So all the parameterization was done by CIDETEC, and the cell was at coin cell level. So we did the parameterization, and then we compute the dimensionless parameters. And what we did for different seed rate conditions, from very, low seed rate to the higher seed rate. And then we identified that there was certain parameters that it was above 1, and even at low seed rate, it was certain limitation. So we know that these parameters, it's related to the concentration gradients along the separator, or in this case, PO and the active material. So, and with this low, so we identified that at low C rate and even at high C rate, we got this limitation. And these parameters relate to the concentration variation along the cell, electrolyte lithium concentration. So what it means is that it is expected to have a very high gradient, and this high gradient might provoke certain limitation because you might be reaching like a electrolyte depletion situation. So what we did later was to validate against the P2D model, and the P2D model, we use our code for that purpose, and as we had all the cell parameters side, we ran the simulation at exactly the same condition of the C rate, from low C rate, 0.1 to 0.8, and as you might be seeing, there is a very huge voltage drop in even at 0.8 C. So as it was predicted by the non-dimensional parameters, there is even at low C rate, like this is the case, 0.1 C, we are seeing very high, huge gradient of the concentration, and at a certain point, you reach this electrolyte concentration equal to 0. That can be understood that it's the final step of the discharge, and this is the case for even at low C rates, but also at very high C rate, in a way that obviously it's more drastic. And even here, what is written is the electrode utilization, so it's only discharge until 0.22. So that means that electrolyte depletion is a very critical aspect in this kind of cell. So then what we did is that to validate against experimental data, so we know that we draw this energy density versus cathode thickness, and taking that into account, what we wanted to achieve is to maximize the energy density, but not only increasing the cathode thickness, but also modifying certain internal parameter, like in the case of the electrolyte concentration. So this is predicted by the models, this plot, energy density versus cathode. And here, this is the experimental work we obtained by performing all the cell configuration testing and analysis. So basically, we can say that the predictions identified in the P2D model were good enough, but also now coming to the non-dimensional parameter, which is this one, we identified that there was certain trend independent on the C rate, that above that value, in this case, which is 1, you were serving certain limitation. These plots represent the relative discharge capacity to these concentration gradients non-dimensional parameters. So above that value, you might be seeing this limitation. And this is exactly what we observed in the experimental part, that there was below the value of 1, there was not limitation, and you could be achieving the maximum capacity, while moving forward to this number, we would be observing discharge capacity reduction. So I think it's a good example how models can provide insight on cell development. The second approach is similar to the previous approach in the neural network models, but in this case, instead of using neural network, we are combining deep learning ensembles and structural regressors. So the first deep learning ensemble was used for classification purpose, which is similar approach to the one I presented before. And the structural regressors were used to predict the energy and power of the cell. And then we made the evaluation of the procedure based on the key fault validation. So again, as I said previously, the methodology was the one shown before. So we ran P2D model simulations, and then with that information, we were able to classify between 1 and 0, depending on if the simulation was finalized or not. And we were able to capture the energy density and power. So with that, we developed a model for classification purposes, and then another model for regression, which is estimation of the dragon plot parameters. So here I'm showing just as an example of the regression algorithms we implement that and then we're capable of reproducing the energy density and power density as in the simulation. So they are very accurate models. I have to say that much accurate than the ones we developed with the neural networks, but it's another example in which we believe the in a way that if it's important, the computational cost, we can supply or we can substitute the P2D model by these surrogate models to perform this design or model-based design experiments. And the third case is about model-based parameterization. And here I'm just showing that in the case of the P2D model, we have the electrolyte, and we need to carry out many experiments to track to identify the transport properties of the electrolyte that are critical, need to be identified for each of the cases that we might be modeling. So in this case, in the P2D model, we have the ionic conductivity, transport number, electrolyte diffusion coefficient, and the thermodynamic factor, 4 parameters. What usually, or the standard procedure for each of the parameters is different. For instance, in the ionic conductivity, we usually assemble symmetric, stainless steel cells, and then we perform the EIS, and then we get the ionic conductivity from the spectra. Then for the case of the transport number, we usually build this symmetrical lithium-lithium cell with the electrolyte case, and then we usually perform the Bruce-Vincent method in order to capture the transport parameter. In the case of the solid electrolyte diffusion coefficient, we also, similar to this configuration, symmetrical cell, lithium with separator and an electrolyte, liquid electrolyte, we perform galvanostatic pulse relaxation method, and then we estimate the electrolyte diffusion coefficients by this equation. And in the case of thermodynamic factor, we use a 3-electrode cell, and then we apply a cyclic voltammetry to estimate the thermodynamic factor. So it's quite a huge number of experiments to be carried out. And then also it's important to track the impact of the concentration, salt concentration, and also temperature. So the number of experiments are substantially increased, and our idea is to reduce the number of experiments required and to be supported by the models-based analysis or models-based parameterization. So if we consider the diffusion coefficient of the electrode, what we usually do is we apply to the symmetrical cell, we apply constant current, and then from the slope of the we apply constant current, and then we perform the relaxation. And while in the relaxation, there is a gradient of the voltage, and then from there we get the slope, and from there we make an estimation of the electrolyte diffusion coefficient. And as I was saying previously, that it's also very important to capture the dependency with the soil concentration and with the temperature. So this is require many cells and many configurations, because it's important to, in the end, to include in the code these dependencies, either by data or capturing or including one equation. So what we are proposing here is a normal methodology, in a way that we have this 1D model, let's say, for the symmetric cell, and then we are applying reduced order models or reduced order methods. So we would have these reduced models, and then we solve optimization problems. So comparing the experimental voltage drop with the ones predicted by the models, and from there we can estimate the parameters. So more or less the schematic is followed, or the procedure is followed like this. We have the full model that it captures the lithium concentration along the electrolyte, and here we have the parameters we want to identify. This is the equation, and these are the boundary conditions and the initial condition for the electrolyte concentration, that is the soil concentration. And running the simulation with this model in Python might take like 10 seconds. So I know that it's not much, but if we need to run many simulations it might take huge time. So the idea is to build a very efficient code or model, but capturing the full accuracy of the model. So what we have done is to build these reduced order models. So we apply this run methodology in the way that we generate certain number of simulations, or what is called a snapshot. And then it's not a very huge number of simulation, it's around 10 or something like this. And then we apply the singular value decomposition. So, and then we identified the modes, what are the modes. And then having the modes, we can apply the POD, for instance, the proper orthogonal decomposition. And as we have certain non-linearity in the equations, we need to linearize the model, and for that we use the IM. So having this, we build these reduced order models, which is basic, and it's much more efficient than the full model. So you can see the difference between 10 seconds and 1.18 seconds. So we make comparison on the results on the voltage profiles and also the concentration profiles, and the ROM model was capturing the full behavior, the full behavior of the foam model. So then what we wanted to perform is to solve the optimization problems. So basically in there we solve once we have the concentration, then we solve the ionic potential equation, and we get the voltage from as it is shown here. So comparing the voltage from the simulation to the experimental one, we are minimizing these differences. We are able to capture or to identify this parameter, which is the effective value of the electrolyte diffusion coefficient. Okay, so we already did that. And what we identified is that we were proposing like a very special protocol for analyzing the symmetric cell, and then we were able to capture and to identify the dependency of the electrolyte diffusion coefficient with different dependency with the concentration. So here you can see that the voltage of the simulation and on the experimental are exactly the same. There's no much difference in there, and that we also capturing this electrolyte diffusion coefficient dependent on the concentration values. So I think this approach might help on the parameterization, because as we need to have like very accurate models, it's very important to have identified properly the parameters, and these parameters need to capture this dependency as well. So sometimes it's quite tedious, and the idea is to use the models to also support on that as well. So as you see that in this case, we only perform one experimental work for the one concentration cell. So we didn't need to run like different concentration cells experimental work. And the idea is to extend this work to further include the rest of the transport parameters of the electrolyte. Okay, so the last point is about the software landscape. And here we might have like commercial tools, but also some open source, which is great, obviously, for the community. So obviously, maybe I miss, and I apologize because maybe I forgot any commercial tool that is not included here. But anyway, what I included is like the most common ones, like COMSOL, Dandelion, Batemo, Bageni, that is made more for BMS control, but they use physics-based BMS control. Python is an open source. BEST is more on the three-dimensional simulation, but it's physics-based. And I think it has like microstructure and macrostructure capturing tool in the BEST tool. And yeah, and then I would like to also introduce our developments in what we call, the name is now Proteo. So if I would like to also introduce a video introducing our tool, and I have to also mention that in this video the tool we have developed is called CIDETEC, but in the end we modify the name, and now the code will be Proteo. So I will run the video, and then I will show the link in case you are interested to know more information on this tool. Let me know if there is any problem with the video, but I will run now.
In an ever-changing context, where immediacy and swiftness are essential to make progress, we want to introduce the ultimate tool that will help you reduce time to market of new batteries. We present CIDEMOD, a battery simulation software promoted by CIDETEC, a digital solution that responds to the most demanding needs of the energy storage industry. CIDEMOD helps material manufacturers, battery manufacturers, and OEMs alike, speeding up battery development safely and accurately. CIDETEC Energy Storage involved 75 multidisciplinary researchers. We developed cells and components in our own battery manufacturing pilot plant, from the earliest research phases to battery pack engineering, through modelling and characterization. Thanks to the knowledge and understanding we have acquired in 25 years of research, we are now able to offer a precise simulation tool based on our own experimental results. CIDEMOD is the perfect digital solution for battery manufacturers, a user-friendly and intuitive software with low computational cost that allows modelling battery behaviour. CIDEMOD is based on multi-physics models and permits the optimization of cell design, considering components and geometry, predicting battery lifetime, and optimizing operating conditions. In addition, your time to market will be reduced by 40%, testing costs will be reduced by 30%, and design time will be reduced by 30%. Our aim is to help you mitigate risks in the search for new battery materials and accelerate the development of new batteries. Together we can grow and keep moving forward, bringing the future closer, faster. CIDETEC, energy storage.
Okay, so as I said, now the name of the tool is Proteo. So, and this is the email address in case you want to have more information on the tool. But now the idea is that there will be a live demo, and for that, one of my colleagues, Clara Ganuza, will be explaining the tool we have developed at CIDETEC. So I give the floor to my colleague, Clara Ganuza.
Thank you, Dimitra and Ellie. I hope everyone can hear me properly. I will now share my screen so that you can see our software. Well, I am going to show you how all of these models that Ellie has explained can be very easy to use with our software. We have developed a web-based application that combines our models and our cell databases in an intuitive and a user-friendly space. This application allows users to enjoy all the advantages that modeling has to offer without the need for advanced knowledge in the field. So the fact that Proteo is hosted on a website makes it easy to use. You don't even need a high-performance computer to make use of Proteo. So as you can see in the main page, we have divided the use into design and simulation. Let's say we're looking for a battery that must meet some specific properties. Our first step could be the cell design, in which we would choose the chemistry to be used or the thickness of the electrodes. We would even like to know the most important parameters involving the final properties of the cells to optimize them. All of this can be done in this first option we name design. When the properties has been chosen, the next step is to know the range of performances of our design. And for this, the simulation option will allow us to define the test to be carried out on the created cell, and within a short time, we will know the results. Different test plans with different currents and voltage profiles can be done, even impedance spectroscopy tests can be designed to know the cell behavior. So we are going to do today a demonstration of how easy it is to optimize some cell parameters. So for that, let's go into the design part. Okay. Right here. As you can see, we find a visualization of all the design tests we have run. Here we can find the status and the time that's going on, the launch time and the finish time of this task. We can delete them or access to the task, to the summary. We will show later everything in detail. So if our purpose is to create a new design task, right in the upper side of the web page, we can choose between three options: design optimization, parameter space exploration, and sensitivity analysis. The design optimization, it's a name, its name indicates, creates an optimization problem to minimize or maximize some property to find out the optimum values. I will show later an example for this. Now, for example, when we try to reproduce an experimental result by the simulations or perform an optimization with an overly large number of parameters, we usually need to run many solutions, changing various parameters in order to search the reasonable configurations. As Ellie explained earlier, here we can get some parameters that with experimentation, with experimental results, it's really difficult to get. Parameters space exploration, as I said, perform a coarse mesh in the parameters space and evaluate in each point. So we can think it like a brute optimization or a way to manage a large volume of simulations. Lastly, the sensitivity analysis would perform a study of how several parameters can influence a cell property. This would indicate which of them are critical to be concerned about it in our design. Again, imagine this overly large number of parameters. Maybe it's not necessary to optimize all of them, but if we knew the ones that affect the most, we can simplify our problem. So, as I said before, in the case study of today's presentation, it's the design of an optimization from zero. So for that, we will click the design optimization and name the simulation. We have think to start with a one variable optimization. So let's start with the anode, the thickness of the anode. We recommend naming it with something descriptive for us so that we can recall what it is. But don't worry if the title doesn't get all the details, because everything will be in the test summary we have seen before. So as an example, we have picked 3 different cells. These are from our databases. So we have picked 2 with liquid electrolyte and 1 with solid electrolyte. Just here in the chart of the summary, we can check the chemistries of the electrodes. We can see this, the cathode is NMC811, that we have a graphite silicon anode. For the other cell, it's an NMC cathode. And the last one we'll talk about, there's no separator, and it is a solid state battery. So we'll choose the first one and we move on to the test plan. This test plan indicates the test for we would like to optimize. So we will be optimizing the specific energy of the cell. So we are optimizing that specific energy for 1C discharge. We can have a 2C discharge or 3C discharge. Later, if we have time, we can make another optimization taking one of these test plans. These are the default ones. Of course, you can upload some test plan files, or you can design it on the tool. For this default test plan, we contain the initial state of health of the battery, the initial state of charge, and of course the room temperature in which we want the experiment to take place. So let's move on into the simulation options. As Ellie explained, our model can be run into P2D, P3D, or P4D scale, and we can add several modules to make the model more realistic. We can add the thermal module, which solves the temperature along the cell due to the internal resistances and the current through the cell. We can also solve the mechanical module, which solves the mechanical stresses due to diffusion ion inside the electrodes. Or we can add the degradation models, such as loss of active material or loss of lithium inventory, we have say growth layer or lithium platinum. All of these modules can be combined as we want to obtain more accurate results. So for the sake of simplicity, we just take the simple P2D electrochemical model. So it's faster and we can see more results. And last, the optimization options. The code, I want to mention that the code is parallelized. So there's really fast in the optimizations. We have a 4-variable optimization. It takes like 30 or 40 minutes, so it's quite fast. Also, we can choose the algorithm to optimize, the optimizer. We can choose between a genetic algorithm or a simplex method or a hybrid global and local. As you may know, a genetic algorithm, which we are going to use today, it's a global optimizer. This means it will explore the whole parameter range. It doesn't depend on an initial point. On the other hand, simplex method, it's a local optimizer, which we have to introduce an initial point, and thus will condition the solution. This kind of optimizer will be faster, but we won't ensure that they get the global optimum. Or the hybrid optimizer that runs a genetic algorithm at this start with a really high convergence tolerance, so we can take the best results. And for that point, we can take it as an initial point and make a local optimizer. So let's pick a genetic algorithm which have these 4 parameters. If you hover with the cursor, we can see what is all of these parameters, like crossover probability, that is a genetic operation used to combine the genetic information of 2 parents, is the probability of, let's say, 2 individuals to have the next generation, or the convergence tolerance for a stopping, like a stop criteria, and the maximum iterations in case that the convergence doesn't reach an end or doesn't get that tolerance. At 20 iterations, the optimizer stops. And the population size. So the optimization needs an objective function and the design variables. We have only available yet the specific energy. There will be more objective functions that we can make a multi-objective optimization in which we can pick the objectives and give them a weight, so we can say which one is more important to us for fitting, and then of course maximizing or minimizing the function. And the optimization parameters, we have to pick this time, as we are going to optimize the anode thickness. We pick it, and of course select the range. Be careful with the units so you don't mess up. We're going to go to the range 1 micrometer to 200 micrometers. And yes, one thing you have to have in mind is that the only parameter of the cell that it's going to be optimized, of course, but that we have a variation in it, that will be the one we have selected. All of the others will remain constant over the optimization. So we have, oh, I forgot to mention the property. we have added a property for the problem, the cell balancing. When we have more than a variable selected on the optimization parameters, we can give the balancing ratio for the cell and choose which one of these parameters we want to get that constraint. So this is a constraint for the problem, for the optimization problem. Later, we will see some results that we have used this balancing ratio. So at this point, the entire problem is set up and we can go up here and press start. It will appear here in the list of design works, and we can check whenever we want the status. Even we can enter the simulation, and we can see the summary for this problem. So the cell, the reference cell we have picked, the test plan for which we are optimizing, the models, there will be a summary of all the models we have picked. Of course, the objective function, we have picked the specific energy, if they are maximizing or minimizing the parameters, we are going to obtain the optimal values and the properties of the cell. This will appear the cell balancing in case we have picked it up. So we can make another optimization. We can create this time one with the anode and cathode thickness. So let's pick another cell. I prefer liquid electrolyte cell from the NMC cathode. Let's pick a 2C discharge with 100% of initial shock. Let's continue with a P2D with just the P2D electrochemical model. And in the optimization options, again, the specific energy as objective function, make sure it's maximizing it. Let's pick both thickness. Remember to select the range for the variables, and we can pick the balancing ratio. For this time, we could choose a cathode thickness for the restriction. Again, a genetic algorithm. I just keep going with the default settings. So then again, start simulation, and then we have both optimization problems here in our design task list. So as we can see, the status of the first one has get to the 5%. This percentage here, it's in relation to the maximum number of iterations. So as we can see, the first simulation has been done, and we can see the curve, or we can barely see the curve is making the with the specific energy through the anode thickness. So we can, in here, we have this plot, and we can select which variables are in the X and the Y axis. With more than one variable, I will show you later. And the color, this, as you can see, we have from dark red to dark blue. There's a range of colors, degradation from red to blue, and that is because the red is the highest specific energy, and the blue is the lowest of specific energy that we obtain. So if we change it, we can have the red through the highest value of anode thickness and the blue to the lowest value of anode thickness. So I think these simulations are going on. So let's see some of the results we have previously prepared. I have prepared an optimization with anode and cathode thickness and the anode porosity with the cell balancing. Here it's quite interesting to see that this constraint here of the balancing ratio makes the range for the space of the anode and the cathode thickness smaller, as we can see. So any value outside of this kind of triangle would not achieve the balancing ratio. So that's why I optimize it. It's only picking values from this triangle, let's say. We can change to see the values with the specific energy with the anode thickness, or with the anode porosity, or with cathode thickness. We can take wherever we want, but it is interesting, this graph over here. It can look like a mess, but if you get to understand it, it's quite interesting. So we pick one of these lines. It goes from one value of anode porosity to one value of anode thickness, again to one value of cathode thickness, and finally the specific energy. So it's like an overview. Obviously you can pick the 2D plot as always, but I think if you get used to it, it can be more descriptive. And of course, the optimum value of the optimization is here in this chart. So we can see we have get a 278 batteries watt-hour per kilogram with these values of anode thickness, cathode thickness, and anode porosity. So going back to design, for an optimization without cell balancing, we have performed one optimization for one CD chart with the P2D electrochemical model, maximizing the specific energy and getting all 4 parameters we have available right now. And what we can see is again that the value is the specific energy value is 222 for this certain configuration of this cell. Also, we have made the same optimization, but with the cell balancing with a ratio of 1, as we can see in the summary. And it is interesting to notice that the specific energy, the maximum specific energy that we can possibly get with that cell balance is lower than the one without that constraint. So now let's see how it's going the 2 tasks, designing task we created. So for the anode and cathode thickness with that 2C discharge, let's see that they are getting these points. And again, this graph over here, we can see how it is going. So as you can see, all those equations that Ellie has mentioned before are collected in this simple tool that we don't need to be experts in the mathematics behind them to obtain any solution. And moreover, these solutions are presented in a user-friendly way and easy to understand, so that decision-making can be straightforward with this. Also, this kind of software can reduce the number of necessary tests to design the design processes. So because we can know in advance the cell behavior. So I think, thanks a lot for listening to us, and I will be grateful to answer any questions you may have. Or you can make a request to certain optimization, I don't know.
Okay. So, I mean, this is like a wrap up or summary slide. So basically, we wanted to emphasize that we've been talking about the family of different P2D approach, in which we were showing examples on how we implement, for instance, mechanical model into the P2D, thermal, extending the dimension from 2 to 4 P4D model, also implementing certain degradation mechanisms like the SCI layer growth and active material loss as well. And then some approaches on the surrogate models, and then also mention some information on the data driven, and then a sample on the data driven as well. Sorry, I have realized that I already mentioned everything now, but anyway, so I was mentioning about this P2D model and the family of the P2D model. Then we talk about the single particle models, and we mentioned the single particle with electrolyte. We show a comparison between the single particle with electrolyte and the P2D model at high C rates and the differences we might have observed. Then, as I was now announcing, like we introduced the data-driven models. I also mentioned some exercises we made before with the surrogate models. And then we showed the 3 examples on the application of models. So that were basically 2 for cell design purpose from the non-dimensional approach, and also machine learning approach. And the third case was more on the parameterization or model-based parameter estimation, how these models can accelerate or can reduce the experimental work to estimate properly the parameters. And then also we did this live demo of Proteus software from CIDETEC. So this is a very reduced summary, I would say, but so I'm just approaching to the end, but I would like to acknowledge to all the people working in the modeling, postmortem and parameterization. Also, Idoia Ordan-Pilleta, who is the responsible of the unit of material energy. Thank you.